the process of building a machine learning model to predict the electrical energy output of a combined cycle power plant. Our dataset includes 9,568 hourly average ambient environmental readings, which we'll also use to build and evaluate our model. First, I will be walking you through the problem definition and my modeling approach, then through the feature selection and the consideration which algorithm to use. And then I'm going to show you how I split the data and validate my strategy, how I compare the result and select the final model. Then I will conclude with the model evaluation. So the problem we're tackling is a regression task where our objective is to predict continuous output variable, specifically the net hourly electrical energy output, which is called PE in the dataset. To evaluate our model's performance, we will use the mean absolute error, MAE, which quantifies the average magnitude of predictions errors in a straightforward manner. The dataset includes the following features. We have temperature T, ambient pressure, AP, relative humidity, RH, an exhaust vacuum, V. And these variables are selected based on their potential impact on the power plant's energy output. We will consider several algorithms for the model. First, linear regression, which is supposed to be simple and interpretable, and making good baseline. Second, we are evaluating the random forest, which is a more complex model, but capable of capturing non-linear relationships within the data. We will start with these two algorithms to understand how complex the model needs to be ultimately. Coming to the data splitting and validation strategy, to ensure that the model is robust and that the evaluation is robust, we need to split the data set. I will share my screen and show you how I've done this. So what you see here is the original data set. I'm using Excel, not Python, not any other program, since I have only Excel at hand. I used the randomize function to basically sort the almost 10,000 line items, and then I split them in 80-20. 80% of the data is used for training and 20% for testing. Within the training set, I will employ a 5-fold cross-validation strategy to compare model performance. This method ensures that each partition of the data is used for validation once, reducing the risk of overfitting and giving a better estimate of the model performance. So as you can see here, I divided the data set into a smaller test. That's the 20%, and then the training data, which I used here. All right, so I've applied both the linear regression and the random forest algorithms to the training set using the cross-validation to compare the performance. And the cross-validation results showed that the random forest model has a significantly lower MAE compared to the linear regression model. And this is suggesting that it's better at capturing the complex interactions within the data. Let me share my screen again. I'll show you a quick output of the model. So that's what I got. And so after selecting the best model, the random forest model, I evaluated its performance on the test set to ensure it generalizes well to unseen data. The final mean absolute error on the test set has been confirmed, and the model performs consistently. So I've shown you a snapshot of my result, and in summary, I want to conclude that I followed a structured approach to build and evaluate. a basic machine learning model, again in Excel, since it's the only tool I had available at hand. I carefully selected the features, employed cross-validation, compared two different models, I think I was able to develop a robust predictive model. Thank you for watching, and bye-bye.